Good day, everyone. Today, I'm going to discuss an interesting topic in physics damping in an oscillatory system. We will learn what acceleration means and how damping affects the motion of an object that moves back and forth. Let's start with acceleration. Acceleration is a periodic of repetitive back and forth motion of an object or system around the equilibrium point. For example, when a pendulum swings from one side to another, it oscillates around the center point. This kind of motion is common in many systems in nature and machine. Now, let's talk about damping. Damping is the process where energy in an oscillating system slowly fades away. This causes the motion or amplitude to become smaller over time. There are three main types of damping, which is underdamp, overdamp, and critically damp. This graph shows how each type of damping behaves over time. The blue lines show an underdamped motion. It still oscillates but with smaller and smaller wings. The orange line is overdamped. It returns to rest slowly without oscillating. And the green line is critically damped. It returns to rest the faster without overshooting or oscillating. I discussed underdamped acceleration. In underdamped acceleration, the system keeps moving back and forth, but each swing gets smaller until it stops at the center. This means the object still oscillates, but its energy is slowly lost. Some examples have included a car, suspension, or a pendulum swinging in air. The characteristics of this motion are 1. It includes to oscillate, but the amplitude decreases. 2. The system may move past and back over its rest point a few times. 3 is and the decay rate or how fast it slows down in is lower than a critically damped system. Underdamped equation. The motion of underdamped system can be described by this equation. This just means the displacement x t change with time. The symbols represent different things. Zeta is a damping ratio. Omega n is a natural frequency. And omega d is the damped frequency. A and depend on the starting condition of the motion. So this equation helps us describe how the system behaves mathematically. Is overdamp oscillation. Here, where the system is disturbed, it slowly returns to a rest position. But without oscillating at all, it doesn't swing back and forth. Instead, it gently settles down. The main characters are no acceleration occur. The system moves slowly back to equilibrium, and the decay rate is faster than a critically damped system. Its overdam system, we find two roots, S1 and S2. By solving a quadratic equation, this equation came from the general second order differential equation that describe how the system behaves. For example, in a spring mass jumper system, we can write the equation as then we solve for r using the quadratic formula. The roots help us understand how fast the motion decays, how the system returns to rest. We have critically damped acceleration. This type of damping returns to its equilibrium position as fast as possible without shooting or oscillating. It's the idea case for many systems like shock observed in cars where you want to settling without bouncing. The main characters are no oscillation occur. The system returns to rest in the shortest possible time and the decay rate is optimal. The equation for this motion is to summarize, damping helps control acceleration by reducing energy in a system, whether It's underdamped, overdamped, or critically damped. Each type plays an important role in how system moves and settle. I'm Rigami Joy Alhuno, Wade Schwab Mendel. Thank you for listening.